All right, let me see. So I need to show you guys how to do unit step things. So by this, I mean I want to be able to Laplace transform functions that aren't continuous. And so I'm going to introduce a funny tool to do that. So this is sometimes called a Heaviside function. So I'm going to define a function u of t minus tau. Okay? So think regular time, critical time. And the way we're going to define this function is it's going to be 0 for t is less than tau, and it's going to be 1 for t is bigger than tau. So think the most boring light switch ever. This is a light switch that's off for all of eternity until the one critical time, and then on for the rest of eternity. That's cool with us? It's kind of a silly thing, seemingly. It turns out to be super useful, right? So, first things first, I need to figure out how to Laplace transform this. I'll give you guys the option. Do you want to Laplace transform it first, or do you want to kind of express a function in terms of this thing first? Your choice. Express a function? Okay. So, let me look at my favorite discontinuous function. It's 1 for 0 smaller than t smaller than 2, and it's t squared minus, I don't care, 1 for 2 smaller than t smaller than 4. Oops, you're not allowed 2. You're not allowed 2 twice. And then it's t cubed plus 17 for t's past 4. Cool?
Cool.
All right. So I claim that you can rewrite this in a better way using unit steps. So first things first, when does stuff start to happen with this function?
0.
Yeah, kind of at 0. What is it before 0?
Undefined.
Yeah, kind of not defined. We could, just for kicks, let me make it 1 forever until you get to 2. When we're Laplace transforming things, we won't care what they are for t's smaller than 0.
Yeah.
Right? Because we truncate that crap when we Laplace transform anyway. You guys see that? So let me just write it this way. So first things first, it's 1, right? Okay, so in the beginning it was 1. And then when did stuff change?
2.
At 2, something happened. So I'm going to put a plus u of t minus 2. Okay, so now it would be, so far I've got, it's 1 until time 2, and then it's 2. But you don't want it to be 2. You want it to be t squared minus 1. So I need to put something in here that's going to turn what it was before off and turn what I want it to be on.
Should it be 2 less than or equal to k down? Because you're turning on the 2.
Sure. So in the end here, I'm not going to care. Because what I'm going to do, the next thing I'm going to do is I'm going to Laplace transform this, right? Which means I'm going to take an integral of it from 0 to positive infinity. And the integral is not going to care whether it's one of these at 2 or the other at 2, because that's the area under a point, which I'm going to tell you right now doesn't matter. And then during Dirac delta section, I'm going to tell you is the only. Sorry. Doesn't matter. Okay, so in this guy.
Is it going to be like a t minus 2 squared minus 1?
Okay, so if I put a t squared minus 1, you guys see that? So now that would be me taking, it's 1, and then after time 2, it's 1 and also t squared minus 1. Yeah, so I got to t squared there. I need to turn the other thing that it was before off. So I'm doing minus 1. Okay, so the general form of that is going to be this thing gets turned on, this thing gets turned off. That is crucial. Does that make sense? So to transition from this step to that step, I should turn this step off, subtract it, and then turn this step on. So now when I get to t is 4, I'm going to have a u of t minus 4. Right?
So times
T cubed plus
t cubed plus 17
Okay, so I want the thing I'm turning on is t cubed plus 17.
minus t squared minus 1.
And then the thing I'm turning off is t squared minus 1. Why don't you have to turn off 1?
Oh, I did.
Yeah, because you already been done turned that thing off. You supposed to be on this? So this is the part that got turned on. This got turned off. Yep.
I'm a little confused since one T can be, actually, I guess it doesn't include, never mind. So that's one question.
Cool. And yeah, you're right that these endpoints might be kind of, the equalities at the endpoints might be kind of dorky. So I'm going to put a universal asterisk on these. Sorry, equal signs over here. So those are always going to be, well, except maybe at the endpoints. Right? And we're going to integrate this in a second anyway, and so it's not actually going to matter. So let me convince you engineering-wise that also shouldn't matter. Engineering-wise, you're using this to solve a differential equation, right? So in the most physically obvious case, that's like me looking at a spring and a forcing condition, right? So if I have a spring and I'm turning the forces on that spring on and off, right? That's like I'm touching it, right? I'm kind of handling the spring as it bounces back and forth. Or I'm like putting a weight on it and then pulling it off. Like the kind of classic example is you have a pendulum swinging and a squirrel runs by and like bounces on your pendulum. Because of course that happens, right? I kid you not. That was,
Classic
the,
example.
that was the first example of the first text I taught out of it. I was like, what?
Obviously.
Okay, at any rate, you don't really care whether this squirrel touches it at exactly the time 2 or just the tiniest little bit later, right? You're just modeling anyway. You guys cool with this? Everybody good with the on-off thing? That takes a second sometimes. I like the way your book does this better than the way that previous books do it.
I guess I thought I had figured it out, but I'm still a little confused. That t minus 2, u times t minus 2 times that function in front of it, you're turning it on, but it looks like you're also turning it off. Because if you put a 2 in, that's going to make it 0, then the whole thing will be 0.
So this piece, right, is the switch at time 2. So this is u of t minus 2, right? And then this thing is turning on the stuff that follows it. And the stuff that follows it is, this thing has a positive sign, so it's actually getting turned on. Whereas this guy has a minus sign, so that part's getting subtracted now. It was kind of added out here. When I subtract that 1, those two cancel, and I'm left with the t squared minus 1.
Okay, so like in a practical application, it wouldn't be exactly 2, you're saying? It would be like past 2, it turns it on?
What I'm really saying is the equalities here, whatever order they're like, okay, so if it's 1, well, t is less than or equal to 2, I kind of said, well, at t is 2, I'm going to change this thing, right? So really I should put this equality up here for this one, but I just don't want to worry about it because I'm going to Laplace transform the whole thing anyway.
They even said that you could define it for like a point anywhere, and it's just like, even if it's like a billion, when you integrate that, it's not gonna, because there's no area under.
Yeah. Yeah, so the issue is I could split those out when I'm integrating, and I'd have integrals across, you know, like 7 to 7 of this like weird, but it doesn't matter what's in there, because it's 0 wide.
Why is there no u function times the 1?
Oh, this guy?
Yeah.
Because that one's on at the beginning. Right, so that's just like, the base operating state is it's 1 forever, and then at time 2 stuff changes. Right. If I had a 0 here, then I'd put a u of t minus 0 here. Right, so that'd turn this thing, it'd turn the function 1 on at time 0,
Mhm.
and then at time 2 it'd change which function's on. Let's cool that.